Okay, so we are going to talk about chapter 15 topics today. So this is, I would say, one of the very important chapters in the sense that it will give us more of a practical perspective on what kind of, how do you gauge your experiment, whether it's good or bad, and if at all, when you change a parameter, what is its effect on the your resultant experiment, basically your signal. So, well, the title says it all, basically signal, contrast and noise. And I think first today we'll talk about noise, and then I think in the next class we'll talk about the contrast aspects. Excuse me. So the key points that we would learn from this chapter essentially are noise and it's how that in your experiment and how that relates to different experimental parameters. Can anybody tell me what we mean by experimental parameters in an imaging experiment, let's say? Well, for a given pulse sequence, what are the parameters? Okay, that's one. Sampling time, okay. Right, okay. Right, but not T1 and T2 of the sample. Those are dependent on the sample. So basically, all of these that you guys mentioned. Excuse me. Now, TE and TR, I think the relationship relative to that and your noise is a bit not straightforward. But the other parameters, for example, gradient strength and sampling and sampling duration and sampling interval, etc. all of them are quite directly relevant to the noise that you would see in your experiment. And then, of course, we look at what's called SNR and the way you measure your experiment, efficiency of your experiment. And that's in both your real and imaginary channels, or in other words, basically magnitude and phase images. And then we'll talk about contrast, its optimization, and how things would change if you have a voxel with different tissue properties. And then just briefly introduce what are the effects of, what are the common types of or modes of contrast generation using exogenous contrast agents, meaning the ones that you inject into the body. So, well, any measurement, any physical measurement, you would probably know by now in your experience in sciences that any measurement would have some error. So the how good your measurement is depends on relative to the noise, how well you're able to distinguish your measurement or make your measurement. So let's say in this example, you have basically these peaks in your signal. Let's say this is your signal that you sample from, or this is the induced EMF, and you see these peaks. Let's, for example, see that if this noise is on the order of the height of the peaks, then you would obviously not be able to make out what these the signal or the presence of these peaks. But then, because the noise is at a lower level, you're able to distinguish that this as signal versus this as noise. So the measure basically, one way to kind of quantify your efficiency of your experiment is signal to noise ratio, where noise is quantified in terms of its standard deviation. Now, of course, noise in our MR case, noise has certain characteristics, and we'll come to that in the next few slides. So standard deviation of noise, taking this ratio of signal peak to the, or signal amplitude to the standard deviation of noise, is what's called signal to noise ratio, or in abbreviation SNR.
Is that the peak of signal or the mean of signal?
Well, in this case, I will, well, in this case it's actually the area related to the, it's the average of the signal, you can say. It's the average of the signal in your, in a finite region. Now in this case, it's actually, you could quantify that in two ways. One, the area divided by, actually not the area, in this case it will be just with peak divided by the standard deviation or the root mean squared value of the noise, not the area, peak, in a 1D experiment. Yeah.
Is that something that people use in practice, or we will?
No, that's what we use in practice. Yeah.
Because I guess there is like proportional to something, you know, like a 0.6 times something.
Well, we'll come to that. That's where we'll. So this is noise where there is some signal. This is just in an example or arbitrary example. We haven't really talked about what the nature of noise is in MR itself. So where is the noise coming from? Well, basically you're taking this, you're recording the induced EMF, and that induced EMF is due to the precessing magnetization. Now, because of the thermal fluctuations of the sample, of the, let's say, the precessing spins, you would have the induced voltage would fluctuate, and that's one of the sources of noise. Well, before we get into all those details, well, in the case of MR, or in general, the signal to noise ratio is one of the kind of pervasive parameter that you would see or use throughout your what do you say, to verify whether your image quality is good or not. Now image quality in the sense of signal as well as in the sense of contrast as well. So when you talk about contrast, it's the signal difference between two tissues. Now in the presence of noise, just the signal difference is not enough. You would have to see what that signal difference amplitude is relative to the noise, which is called the contrast to noise ratio. And it's a good CNR and SNR, an image which contains good signal to noise ratio as well as contrast to noise ratio is what the desired outcome in any experiment for us. A good signal to noise ratio doesn't necessarily mean good contrast to noise ratio, but it is a good SNR is necessary for a good contrast to noise ratio. So let's see, we're talking about signal and noise, and it's the ratio of those two that is important in evaluating how good an experiment is. Now, so far we have just been very generic in our explanation about signal and noise. We will come to the specifics now in terms of the MR signal and what the nature of the noise in MR is in the next few slides. So you have from your chapter 7 and 8, your signal is actually proportional to the volume of the voxel, right? So that is, and also it's proportional to square of B naught, and it's also, well, it will depend on the amount of protons that are available in your volume to give you the signal, which is the polarization factor, and the coil, basically coil sensitivity at that particular location of your, from where you're picking up the signal. So all of these are dependencies of signal are present, and of these things that you have control on, so to speak, are, let's say, you can change the B naught at which you do your imaging. You can change the voxel size, spin density or rho naught, the number of polarization or number of protons available to give you this signal. That, I guess, is more or less, well, in this case, I'm sorry, I should take that back. The rho naught in this case is just the spin density, a number of protons per unit volume. The polarization aspect is already taken into consideration by that factor gamma squared H h bar squared by 4 kt. So that polarization aspect is already taken care. So it's just the spin density, which is rho naught. So rho naught is a material property, you can't change that, of course. So beta perpendicular, which is the coil characteristic, which you can change by changing the type of coil that you use. So essentially, and temperature is, well, temperature is of the sample. Typically you don't change that, you don't cool your subject or heat your subject to do your imaging. So essentially B naught, voxel volume, and the coil characteristics. Those are the three things that you have possible control over. And there are other characteristics, of course, that change your signal amplitude depending on your experimental parameters. But essentially right now we are interested in the first, in these dependencies first. So the first important aspect is the volume proportionality, meaning it's proportional to the voxel volume that you're acquiring the signal from. So let's move on and look at, you can realize that voxel volume dependency also from your signal equations, which is where you will see that your in your inverse Fourier transformation you have the delta x parameter explicitly, which is in this case this is 1D example. In the case of 3D example, it's basically proportional to the delta x times delta y times delta z, which is the voxel volume. So both from the basic coil induced EMF point of view as well as from your encoding point of view, it is proportional to your voxel volume. So that's your voxel signal and that's your voxel volume. Now so actually I kind of jumped to this discussion earlier, but so we're now back to that. So the source of noise essentially is thermal noise, basically from the finite temperature of the object, where you so it has finite thermal energy. So the protons, even though they're precessing, they'll have some thermal energy which could be viewed as statistical vibrations of the molecules, which would induce a certain variability, statistical variability in the induced EMF. And then there are other coil related and electronics related noise that can creep into your signal. So essentially what you're getting is the induced EMF signal that you're recording, which can be influenced by all these other aspects in addition to your signal encoding process that you're doing. And there are other possible sources where which is systematic noise, where scanner, let's say the B naught field of the scanner is drifting for some reason, so then your induced EMF would also slowly drift down, because drifting meaning if the B naught amplitude goes down, let's say, then the induced EMF amplitude is also going down, right? Because it's the induced EMF is proportional to omega naught, and if omega naught is slowly changing, coming down, then obviously the induced EMF will also come down. So that's a source of systematic noise. And then AC power, if you have 60 hertz or 120 hertz creeping in. Now in this case it's megahertz, but it can also cause a systematic noise, I mean in terms of our sample signal. And then physiological noise, which can affect and can be systematic in nature as well, which is breathing and the heartbeat related, pulsation related artifacts. We are essentially going to be talking about this, which is the random noise aspect. So while these are more systematic and deterministic, meaning you can actually know what is the characteristic of the noise, there is certain periodicity or characteristic to that noise in terms of features. Whereas in the case of here, the thermal noise, it's quite random, the induced EMF. It's due to the random fluctuations or the finite thermal energy of the body. So the thermal noise can be kind of broken up into these three components that we mentioned earlier, and the noise for any random variable, if you have So the signal is being affected by 3 random variables, and it's the summation of these 3 random variables that you have this signal being affected by those 3, or the summation of those 3. So the net variance of the summed signal is actually sum of the variances of these 3 random variables. So that's from the statistical theory, where if you have 2 random variables and then you add them up, variance of those 2 random variables is basically they add linearly.
So these 3 components are independent or they are dependent?
Independent. So, but what you're measuring is just sigma squared thermal, right? So you're essentially not making a distinction as such in terms of your own measurement. So it's the summation, and it turns out that is actually proportional to these 3 physical parameters, where R is your effective resistance of the coil, and then the BW is basically bandwidth of the coil that you're reading in terms of the number of frequencies that you're reading in, the width of the frequencies that you're reading in, and then KT, K is the Boltzmann constant, and T is your temperature of the coil. So of course you can't change the temperature, like we said. Well, the resistance is actually both due to the coil resistance itself and body loading the coil. When the presence of the coil, in the presence of the body, the coil would have a different because of the induced inductance or coupling of that body with the coil. That effect would change its resistance. So that component of it, and then the electronics resistance. So that effective resistance is what this particular parameter is proportional to, meaning that the noise variance is proportional to this particular product. And bandwidth coil is basically the bandwidth that you're using to read out your signal, essentially. So that's one thing that you have control on, right? You can change your bandwidth by changing your gradient or your sampling delta t rate, etc. So but note that this is actually the noise in K space that you're sampling, or that you're obtaining, not the noise in image domain. So what is relevant for us is actually the image, the noise in the image domain, what is the nature of that relative to the noise that is being recorded in the K space. So this dependency that you see, this is the noise dependency in K space. Of course, you can imagine to reduce the effect of sigma squared, you can reduce the temperature of the coil, which in turn will reduce the resistance of that coil. So you can actually do that. Well, this temperature is actually samples temperature, I'm sorry. So this R is the resistance, this whole resistance, and then this you can reduce by reducing the temperature of the coil, right? So, and cryogenic coils are used in NMR, where the coil is actually cooled so that your induced EMF is higher, you have better signal to noise ratio. Okay, so if you model, like I said, this noise is actually in the K space that you're recording this. So you can model your signal as the linear summation of your actual signal without any noise, with plus the epsilon K, which is the noise parameter. Now for thermal noise, which is basically it's random, and one of the characteristics of that noise is that the power spectrum of that is constant across all the frequencies. And if you take the frequency or probability density function of such a noise, then it would appear as Gaussian, so if you have noise something like this, if you look at the probability density function of that noise, or in other words histogram of that noise, then you would see a distribution something like that. So white noise is essentially the mean of that noise. It's basically fluctuations about a mean value of 0, and that fluctuations are quantified or parameterized by the standard deviation sigma m. Okay. If you look at this, its distribution, it's Gaussian distribution, and this is the width of that is what gives you the sigma basically. So 1 sigma, 2 sigma, etc. Now, if you take the Fourier transformation of that, or inverse Fourier transformation in this case, then you would notice that the amplitude is actually lower, which is this is total 10,000 points. You started with an amplitude of a sigma of 1, standard meaning so this sigma for this distribution is 1, and you see the sigma of this noise in the image domain is actually 0.01. So you see that it's decreased. Now we'll come back to that, how that happens. If you take the autocorrelation function and then take the Fourier transformation of that gives you power spectral density, or basically which is constant for a white noise. So let's look at this math that's given here. So the autocorrelation function is this is the random noise, and this means the mean value of that, and that turns out to be constant at any value tau. So if you take that Fourier transformation of that, then you basically get an impulse function. Now when you let's go back. It's this eta parameter that we're interested in. Eta x is your image domain noise. Epsilon k is your k-space noise. Now it's these two that how this relates to this in terms of the standard deviation of this, how that relates to the standard deviation of eta x is what is of importance for us. And we already saw empirically that if you take this noise and you inverse Fourier transform it, the standard deviation almost is reduced by a factor. You can actually derive that by looking at the Fourier transform relations. So you have the eta p delta x, which is the inverse Fourier transformation of epsilon k, and if you take the expected value of that noise, then the expected value of noise in the k-space domain is 0. So it also turns out that the expected value in the image domain is also 0 of that noise. So this is the image domain noise, and the mean value of that noise is 0. The variance of that, all of this math that we looked at, one second, so let's just go back and just bear with me here a little bit. So this part you will see that you will end up writing that when you write this Fourier transform integral of this epsilon k, and you will see that since the expected value of that variable of that autocorrelation function is sigma squared m, you end up with sigma squared m this, but with the factor n, because essentially if you look at your Fourier transform expression, it is averaging of all these values in k space, and then getting the value for a given voxel for different k values, right? So in that sense, I mean, just to get a intuitive understanding of that, you can go through the rigorous math and arrive at the same result. But to get an intuitive understanding of that is what I'm trying to tell you, that when you do a Fourier transformation, essentially you're adding up all these signal contributions with different weights at each frequency, and then dividing that with n, and to get your value at a given value of x. So essentially you're averaging the signal that you sampled in your k space in some sense. That's why your noise variance in image domain is actually 1 by n factor of, meaning the noise in image domain is actually one nth basically. So number of sample points that you sampled appears in the denominator. So sigma squared by, if sigma m squared is the measured variance in k-space noise, then the noise in the image domain is sigma m squared by n. That's the variance. So in terms of standard deviation, it's basically sigma m divided by square root of n. Now I know that probably is not clear to you guys. I guess you would have to go through the math to understand that part. But this is quite interesting, and you will see that this has influence on your experimental parameters that you choose. So essentially, white noise in k-space leads to white noise in image domain, and the noise variance is divided by n, where n is the number of sample points that you sample and subject to the Fourier transform. So when you Fourier transform, you are essentially reducing the noise in the image domain by square root 1 by n basically. Okay, so if you want to improve your signal to noise ratio, then one of the ways is obviously to take multiple measurements and average them. So when you do that, you're essentially taking multiple signal samples, summing them up and dividing by nk. So that's your if you don't have any noise, that's your sigma, that's your m, and so that's your ideal signal. And then the noise, of course you're adding up the variances and dividing it by n as well in your averaging process. And if you want to take the standard deviation, then you take the square root of that. So that becomes, if all the variances of the individual acquisitions is not correlated, meaning that the noise in one acquisition is not correlated with the noise in the other acquisition, then you can do this summation in quadrature. And here we're assuming that the noise is same in each instance, meaning that the noise variance is same in each instance. So that's why this becomes is that right? Hold on a second. Every time I get confused in this. So this is n sigma squared, right? Hold on a second, let's write this up here. So you're adding up signal So if all of these signals are same, you have n si k. Oh yeah, I think that's kind of the wrong way of expressing that. So if you're not averaging it, let's just say adding up, that's way, I mean, it's easier to look at it that way. So s multiple measurements, you're adding net is basically sigma I equal to 1 to n. Now if all of these are same, then what you have is Sn times Sk basically, right? Now if you look at the noise, then noise variances also get added up in quadrature. So if all the noise variances are same, meaning that sigma 1 squared is equal to sigma 2 squared, so on, then this becomes n sigma squared, and sigma net becomes square root of n sigma. Now the new noise, new signal to noise ratio now, SNR, is n S of k divided by square root of n sigma. So your signal to noise ratio has improved by square root of n S of k. Sorry. Yeah, noise is reduced by factor 1 over square root n. So that's Sk by sigma. That's your original SNR. with one measurement basically. So with n measurements, your SNR is improved by square root of n. In other words, you can say that the noise is reduced by square root of n. That's what we're trying to get at. I think I mistyped that. So this is true for any image domain or k space. Doesn't matter. The signal, we just wrote it as S of k, but it can be S of x as well. I mean rho of x as well. Okay, was that clear? So, and like I said, this is valid once only if the individual measurements, the noise in the individual measurements is uncorrelated.
So how about when they are correlated?
Then I think the summation is actually not straightforward. The variance doesn't just get, it's not sigma 1 squared plus sigma 2 squared. You would have to look at the what is that, cross correlation of those noise terms as well. So I think you'll have 2 sigma 1 sigma 2 and then so on the other terms. Right. In general, when you do individual separate instances of measurements, then the noise is typically uncorrelated. Okay, so so to improve signal to noise ratio, of course, averaging is one. But you can average in your k-space acquisition, you can average that data in multiple ways. Well, so one of the ways is to do long-term averaging, meaning you do the experiment once and then do the experiment again, in the sense that you're acquiring multiple k-space lines. So you can acquire first k-space line, second, so on till n, and then follow it up with the next k-space line, next acquisition. N acquisition 1, N acquisition 2, and then you can average that. That's long-term averaging, meaning that you're acquiring one full data set every time, and then you can save that. Whereas practically speaking, well, both of them can be done, but in this case, typically to save memory, you can do first line and then acquire the same line without changing the phase encoding step the next time, and then just add them up. So that's called short-term averaging, and that helps you save memory basically. So in that way, you won't be saving the individual acquisitions. You will basically end up with the averaged output rather than the individual acquisition images. So I mean, there are advantages for both, where if you think that you don't want the object to move from one acquisition to the next, meaning object motion is of course undesirable in this case. Let's say in your experiment, then you want to kind of improve your signal to noise ratio by acquiring the data. Well, I think it depends on the situation, but you can do either ways. Just quickly acquire the consecutive k-space lines, and then do the repeat acquisition of the next one, meaning the next an acquisition for the average, so that first time when you're acquiring the signal covering the k-space, even if there is slight motion, you won't have that much of an effect. Whereas if you're spending time to acquire, let's say, same phase encoding line 3 times, and then next time same phase encoding line another 3 times, and if there is motion, then obviously you will end up with a data which is quite blurred. You get the point. So let's say you're imaging a fast, let's say heart, okay, for example, that's one example, or well, you can say the fetus as well. That's because you have the option of the baby moving. So typically you want to do long-term averaging, where every time you're acquiring one data set, you don't want the object to move, right? So you want that to be fast, your acquisition. If in case the object is not moving and everything is stationary, then it doesn't really matter which way you do, and you can save the memory by using the short-term averaging option. You understood?
No, I didn't get it. So which one is in favor of motion?
Long-term averaging, because you can acquire, so a single acquisition will take shorter time, right? So then you're acquiring the second acquisition, the same phase encoding everything, but even if the object moved, then obviously you will have a different spatial location of the object in the second acquisition, But you can obviously then co-register and then do the averaging part. But you don't want the object to move while you're doing your encoding of your k space, right? So that's one example.
Why is the acquisition time is lesser in long term?
No, it's not. No, it's not acquisition time being lesser. The acquisition time is always going to be for a 2D. Let's say it's ny times tr.
Yeah, that would be so.
Now in this also it's ny times tr, but then because you're acquiring ny 2 times, so it's actually 2ny times tr to collect the full image in this case.
Okay, yeah.
So you're still collecting the same k space, but then you're collecting every phase encoding step twice in the second option. If the object is not moving, for example, you're imaging your brain, it doesn't really matter. You can do short-term averaging, save memory, and it'll be good basically. So it doesn't really affect your output. So well, the noise again decreases, or you can look at it as SNR increases by square root n. Now there are other ways of improving signal to noise ratio using phased array coils, where if you remember the first slide where you had sigma coil and then sigma body and then sigma of electronics, right? So if you have a large coil, typically the birdcage coil, the whole sample is coupled with the coil, meaning that the body related noise is quite large because of the spatial extent of the coupling between the sample and your coil. If you have a much smaller coil, then the coupling between the space that this coil is covering spatially, for example something like that, so the coupling between the space that the signal from which the coil is picking up the signal is effectively smaller. So that means the body contribution of the noise is reduced. So you would have lesser noise when in the region which is closer to the coil. Well, in other words, actually it's not lesser noise, it's actually higher signal sensitivity essentially. So the noise essentially remains the same, but the coil is more sensitive to the signal, to the locations of the object which is closer to the coil. So the beta 1 parameter essentially is spatially varying. So if it will look like something like this. Well, I guess you should probably switch off the. Can you see the images? I think it's the first one. Okay, let's go. I think that's good. No, these guys need the light. You're okay? Okay. So, for example, you can. I mean, this happens in phased array coils, but also think of the most recent application of parallel imaging, where you're using phased array coils to actually speed up the data acquisition. But I think let's consider just the phased array coil example, where each coil is picking up signal from a spatial location which is closer to it, and then the signal which is far away from the coil is quite low. So the noise is same throughout the field of view, whereas the signal is higher here compared to here because of the coil sensitivity. So in that case, how do you combine these coil images to get the optimal signal to noise ratio in your experiment? So ideally, so far we have just talked about one coil. Typically it's a birdcage coil. So far we have talked about essentially, which has a uniform B1 reception, and your noise characteristics and signal pickup characteristics are uniform throughout the space. Whereas in this case, of course, your signal reception, the B1 profile of the coil, or beta 1 profile of the coil is spatially varying, right? So how do you combine these individual channel images to get an optimal image with uniform signal sensitivity and noise as well? So it turns out if you work out I think it's one of the homework problems, I guess. If you work out the way to combine these images, the optimal way is not simply adding them up. In fact, it's actually the sum of squares of these coil images that gives you the optimal signal to noise ratio. So that's just for the magnitude of the image. So that is actually a consequence of your so essentially it's the way noise gets added up when you add these images linearly versus when you square them up and then add them up. So you have different so the noise contribution is different when you do what you call a linear combination versus sum of squares combination, and when you work it out, you'll see that the signal to noise ratio works out optimal when you do the sum of squares combination. That's just for the magnitude part.
It seems when we add the noise linearly, we have more chance to cancel out noise, because maybe the negative part can cancel out the positive part. But when you square them, all the
well, here we're just talking about magnitude, so it doesn't have the negative part. It's just the magnitude that you're combining. So you
mean that the noise that we have is always positive?
In the real and imaginary channels, it's always positive and negative, you can say. But then when you combine when you create the magnitude image, we'll come to that. In fact, it turns out that wherever you have signal, the noise distribution is more Gaussian around the signal mean value, whereas when you have no signal, the noise distribution is actually Rayleigh distribution. So we'll come to that. There's a slide on that. So in the real and imaginary channels, the noise is actually oscillating about the zero signal point, whereas when you take the magnitude, the distribution is slightly different when you plot it out, basically. So it's more like the first profile that you saw, where you have the peaks and then you just have the noise there. So it is still about a baseline. So to measure signal to noise ratio, typically what we do is, and that's coming back to Mahmood's question earlier, if you have a homogeneous region in your image, then you can take the mean and standard deviation, or look at the histogram of it. If it's a homogeneous object, then the signal should have been flat in the absence of any noise, but then you will see that it's a Gaussian distribution. So that means that width of that, so one standard deviation of that Gaussian is the standard deviation of the noise. However, in human images, in general, it's very tough to get a homogeneous region to measure noise. So one of the ways to do that, to estimate the noise variance or noise standard deviation, is to measure the noise in the background, where there is no signal. So it turns out the noise in the background region is actually Rayleigh distribution, whereas noise wherever you have signal, turns out the signal to noise ratio has to be, so any SNR where any signal to noise ratio greater than 4:1, the noise distribution in the signal region is always going to be Gaussian. I think, is it 4:1 or 5:1? I think it's 4:1. I can come back to that in the next class. I can let you know. So, but the Rayleigh distribution in the background where there is no signal, the standard deviation of that is related to the standard deviation of the Gaussian noise, which is in the signal region, is related by this expression. So basically the signal noise in the background, noise in the object is actually higher than the noise in the background. So this is the noise in the object, this is the standard deviation of the noise in the object, or where there is signal basically, whereas this is the noise standard deviation in the region outside. So that's essentially Gaussian versus Rayleigh distribution, Rayleigh being in the background region and Gaussian within where you have the signal basically. So you can actually measure the noise if you want by repeating your experiment n number of times and then subtracting it and see what is the noise standard deviation or variance. There your signal is always the same, right? So it's only the noise which is uncorrelated. Now in case basically when the noise is uncorrelated from one acquisition to the next acquisition, then the subtracted image will have actually square root of 2 times the original standard deviation in a single experiment. Now this is a consequence of basically this summation where you have n sigma squared, where each sigma in this summation each sigma is uncorrelated. So if you have 2 acquisitions, you have 2 sigmas, two such values, and whether you subtract or add, the variances always get added up. When you subtract or add 2 random variables, the variances always get added up. So basically, variance is n sigma squared, in this case 2. So when you take that and you get the square root of 2. So that's why you have the square root of 2 sigma naught when you have multiple acquisitions. 2 acquisitions, and then you're trying to subtract that. And you can see you can measure the noise variance from here and then estimate the noise variance for the single acquisition. Now that is of course time inefficient, because you'd have to do the experiment twice and it doesn't really make sense for you to be able to do that. So typically we just go by measuring the signal or noise variance in the background and then estimating, using this relationship, estimating the noise within the object. So collecting multiple times is quite time inefficient, but that's something you can do. So in fact, if you see this image, you still see the structure here, right? So that's not quite normal if you just had completely uncorrelated noise. In fact, this is an example where the noise is quite slightly correlated spatially. That's because this is acquired using a phased array coil, and when you do the combination of coil combination based on adaptive combination, not sum of squares, but an adaptive algorithm, that's what typically is being used on the consoles today, the noise variance in the background region is not particularly Rayleigh, and there is some noise correlation spatially. When you do that with a birdcage coil, so this object, you image them twice and then you image it twice and then you subtract it. So here you don't see the object, right? You just see the noise, which is more or less, but then you see the boundary roughly, right? You can make out the boundary of the object. That's because, that's mainly because the noise in this region has slightly different distribution compared to here. Like I said, this is Rayleigh and this is Gaussian. So this is basically image twice and subtract one from the other. This is what you would get. And so this is the noise, signal distribution around the mean value. Sorry, Emil. Okay, I think that's fine. So this is single acquisition. You subtract the next acquisition and then you get that. And basically this is the distribution or histogram of the signal voxels in the background, whereas this is the histogram of the signal in this. So the mean value corresponds to the mean of the signal here. This region is homogeneous, so you can take the standard deviation as this sigma naught. So the standard deviation of this and this are related by the expression that you saw earlier, which is actually, that's here as well. So you can estimate for wherever you have non-parallel imaging, where the image is actually reconstructed through sum of squares, where the noise behavior that we saw, the background is Rayleigh, and then the noise inside the object where you have signal is Gaussian distribution. That rule more or less is agreed. I mean, is followed in an image where the image is reconstructed using sum of squares approach. For phased array coils, for birdcage coils, this rule more or less applies. That rule applies for birdcage coils, which you typically use for imaging in 1.5 Tesla. Nowadays in 3 Tesla, more or less most of them are phased array 12 channel or more type of coils. So there you would have to be careful when you try to quantify the noise characteristics. Even there, even if it's adaptive combination, the noise within the signal region is still Gaussian, but the noise in the background region, where there is no signal, that is not particularly Rayleigh distribution. So you want to be careful when you take noise, when you want to estimate noise from the region in the background, and in case where it's parallel imaging, or in case where the image is being reconstructed using parallel imaging. So just to kind of summarize what we saw, voxel signal of course is, what we went through until now. Voxel signal is of course proportional to the volume of the voxel. Then the noise standard deviation sigma in the image domain is 1 by n square root of n, the number of sample points relative to the noise in the K space. We also saw that if you do the averaging, then noise is reduced by square root of n, and noise is actually proportional to the square root of bandwidth, or this is standard deviation. So now if you combine all of these to look at what is the impact of these dependencies on the signal to noise ratio in your experiment, then you would end up with an expression something like this, where your signal is proportional to the voxel volume, whereas your noise, which is inversely proportional to n acquisition and nx and ny, or so I've written that for 3 dimensions, but you can imagine just remove y and z and then you're there for 1D. So so that expression is one of the key expressions that you would be using to estimate how your signal to noise ratio would change relative to your starting point. For example, you start with a certain experimental setup, and then you want to change a certain parameter. For example, you want to change your resolution, or you want to change your field of view. What effect that would have on the other parameters is in terms of signal to noise ratio. This expression kind of summarizes that. And you can actually play around with this expression quite a bit in terms of looking at different scenarios. So you still have to go through your, follow your Nyquist relation. So using that, you can substitute for bandwidth read. So if you substitute for so nx times delta x, well, not nx times delta x, sorry, in this case. So this goes to the numerator. This is nothing but your bandwidth, total bandwidth of your bandwidth read basically. So this is this, so that's equal to 1 by delta t. So in this case that's 1 by square root delta t, so that goes to the numerator, and you end up with this expression. So in other words, and if you multiply with this nx and t, as you combine that, nx and delta t, that's your total sampling time. So your signal to noise ratio per unit voxel is proportional to the time you take to sample your signal. Of course, and that's if you keep some other things constant. So this expression, you can use this provided typically when you want to keep one thing constant and change something, then what is its effect on the other parameters? Let's say you want to fix your field of view but change your resolution. So what other parameters do you need to change to keep your signal to noise ratio same? Or if you change nothing, then how is your signal to noise ratio going to change? Is it going to increase or decrease, etc.? So so this is basically to say, so these relations remain in the sense that this and this is what these are always true, meaning basically as long as you follow the Nyquist relation, these are true, and this is your signal to noise ratio proportionality that will govern how your SNR would change if you change one of the parameters while following these relationships basically. So if you want to consider, in the textbook there are quite a few cases, but I'm just going to go just one case where, so one or two cases I think. So here you have in your experimental setup, we're just looking at 1D case where you have your voxel size, your number of data points that you're sampling, field of view, your read gradient, your sampling duration, sampling rate or inverse of the sampling rate I would say, that's delta t, and then your total sampling duration and how your SNR basically. So if you take this as your starting point, meaning this was your initial reference point, and let's say you want to reduce your voxel size, and what do you do? So you can reduce your voxel size, and if you keep your number of sample points same, then you would have to reduce your field of view, right? That implies that your field of view goes down, provided you keep your gradient same. And the other scenario is you reduce your voxel size, meaning you're increasing your resolution, still reducing your field of view, but you can bring that about by now in this case you're changing your gradient strength by twice. So what is the output in terms of what is your resultant SNR? So here when you keep all of these same except you change this, then to follow these relations, following these relations, you would have to increase your sampling duration by twice. So the total sampling duration is twice. So then your signal to noise ratio is 1 by square root 2, meaning square root 2 worse. Whereas in this case, you're changing your voxel size and by reducing your field of view, keeping your matrix size constant. So you can do the same. So if you look at these three, delta x by 2, these three terms, they are the same in both scenarios. But then you're bringing about that or implementing that by doing two different things, and it has different effect in your signal to noise ratio related to your starting point. So this is just one example where you can relate how you can bring about the same effect by varying multiple other, one or two other parameters, and which parameter you want to change is a function of what is your application and what is your trade-off. So in this case I'm taking twice the sampling time, right? So let's say my sampling duration initially was 10 milliseconds, now it's 20 milliseconds. Now T2 star of the tissue is, let's say, about 25 milliseconds. Then your sampling duration is on the order of T2 star, then obviously you'll have a lot of filtering effects, right? And so that you wouldn't want to do this. So now in this case you're increasing your gradient, right? So you're increasing your gradient, so basically you're half worse your signal to noise ratio, but then your T2 star effect is not that bad, meaning that your TS is same, so your T2 star effect remains the same related to the initial scenario. So what is more important for you? Is it to avoid T2 star effects or get a better signal to noise ratio even if the T2 star effects are okay, acceptable? Or you can live with worse SNR, but you want to keep the same signal to same sampling duration and still do higher resolution imaging. So Those are the two scenarios. Things, is it clear to you guys? Right? So this is one scenario, and there are multiple other scenarios you can imagine where, let's say, you don't change your field of view suddenly. I mean, let's say in this case, you want to reduce your voxel size, but you don't change your field of view. What are the other parameters that you would change? And you can come up with which is the most efficient. If you change one, well, in this case we are just talking about doubling, which because it's easier to work out the factor 2, but you can change it by typically you could also change it by a fractional number, right? When you change a value, your SNR would change, and how much and how it would change is governed or is guided by this expression. And all of this is subject to following these relationships. So that's one example where you would see. I mean that's typical calculation that goes on in the scanner when you change, for example, on the scanner, when you sit on the scanner and then you change, let's say, your field of view, then you would see that suddenly your signal to noise ratio has changed. So how do the scanner calculates it? How does it calculate? It will calculate in this manner. Now suddenly your signal to noise ratio has gone down if you increase your field of view. That means scanner doesn't know what else to do. It's just changing the parameter that you're telling it to change. So if you change the field of view keeping everything constant, everything else are the same, then your meaning the matrix size same, you increase your field of view, then your signal to noise ratio is going to increase. Let's say you decrease your field of view keeping everything constant, then your signal to noise ratio would decrease because your voxel size has decreased. If you want to bring back the signal to noise ratio, then you would want to change, let's say, the gradient strength. So that would change your bandwidth. In other words, you want to change your bandwidth to keep your signal to noise ratio same, or you could increase or decrease your matrix size to keep changing nothing else, reduce field of view and decrease matrix size. Then your voxel size remains the same, then your SNR is going to remain the same. So all of these calculations are happening in the background in the scanner when you are changing these parameters, and you would have to keep that expression in mind when you want to, let's say, bring back or do the optimal combination of parameters to make sure you don't lose much. So for example, you change something by double, the worst that you can do is square root 2. So you can aim to get to square root 2 by, then you will know, okay, what other parameter can I kind of keep constant and change the other one to not have half worse but square root 2 worse only. Or if you want to keep this SNR same, then you can figure it out anyway. So all of these combinations is what I'm talking about. This expression would be useful for you. Now if you just look at the SNR per voxel along the phase encoding direction, it's basically dependent on the number of sample points that you are sampling. Again, in this case, you can change your field of view or voxel size, or the number of sampling points to change your SNR per voxel, per unit voxel in your phase encoding direction. And just like what you saw earlier, you would have the trade-offs in one scenario versus the other. So in a 2D experiment, let's say you're doing, so basically in a 2D experiment, this expression changes slightly to this, where the Z part changes to TH, which is the slice thickness. And that's the expression for signal to noise ratio per unit voxel in a 2D experiment. Compare that with the 3D experiment above. So if you want to image the same slice thickness or same slice, and you can do 2D or 3D experiment, and you have a lot of time. Then if you do the 3D experiment, then you are square root NZ better off in signal to noise ratio. If you observe, so this TH is delta Z, right? So if you look at these two, well, N acquisition is equal to 1, let's say, sorry. N acquisition is 1, so this is NY times TS. You have the square root NZ additional factor here, right? So if you do a 3D experiment, your signal to noise ratio is better off by square root NZ. Whereas if you do a 2D experiment, you don't have that factor, you just have this. Compared to 3D, it is square root NZ worse off, right? Now, but you just think about it, it only takes ny times tr to collect this data, whereas this is ny times nz times tr to collect that data. So if you have time, then you're always better off to getting better signal to noise ratio. That is everything, all the other parameters, t, tr, everything else is same, just these two are changing. Then you're always better off doing a 3D experiment if you have time. Now if you don't have time, then there are other calculations. So typically the way you counteract that effect of lower signal to noise ratio in 2D is you use a longer TR. Now the dependency of your signal on the TR is a little bit non-linear, but typically the longer the TR, the better is your signal to noise ratio in 2D experiments. So remember what we went through in chapter 10, I think, the multi-slice imaging, where you do longer TR and then excite multiple slices within that TR. Right, so long TR allows you to do two things. One, it will give you better signal to noise ratio for a given imaging experiment in a 2D experiment. And well, in general, in the imaging experiment, longer TR typically gives you better signal to noise ratio. And well, I have to qualify that this is typical gradient echo, spoiled gradient echo kind of example that I'm talking about, or spin echo examples. So basically, if you use a longer TR, you can do two things. One is better signal to noise ratio due to the longer TR, and you can do multiple slice excitations, so you can acquire multiple slices within that TR. So those are the two things that are advantageous when you do longer TR, and that slightly counteracts this square root NZ effect compared to 3D. So if you're debating whether you want to do a 2D versus 3D experiment, and you don't have as much time to do a full 3D experiment to collect the whole slab, then you can do a 2D experiment, but a slightly shorter time, as long as your TR is quite is longer, typical compared to a 3D experiment. Now, in the case where NZ times TR in a 3D experiment, not TS but TR, that's the imaging duration, right? So NZ times TR in a 3D experiment is equal to the TR of 2D experiment. Then more or less these two applications, these two 2D versus 3D are equivalent. We talked about this similar approach last time as well in one of the classes in terms of the imaging time duration, right? So if NZ times TR is in a 3D experiment is equal to, in a 2D experiment the TR is equal to NZ times TR of the 3D experiment, then the imaging time is the same. Okay. Then here signal to noise ratio wise nothing else changed, right? Because there is no NZ here to change your signal to noise ratio for a given slice. You guys following me here? Okay. So essentially what I'm talking about is TR2D is NZ times TR3D. Okay. Under this condition, is the signal to noise ratio of the 2D going to be any different? Right? No, because nothing else changed. Delta X, delta Y and slice thickness hasn't changed. NY times TS sampling duration has remained the same. It's just the TR that I'm talking about. Now, what I'm trying to impress upon you is that this longer TR compared to the TR of the 3D experiment is going to give you signal to noise ratio boost, which is not seen or expressed in this expression. So you would come to that, I think, in chapter 18, where you see that the effect of TR in your imaging experiment. So the longer TR typically gives you higher signal to noise ratio. So that's what I'm trying to refer to here. So if you want to do an equivalent 3D experiment, 2D experiment for some practical reason, then typically if you follow this relationship, then you would have similar signal to noise ratio, not same but similar signal to noise ratio as a 3D experiment. So signal to noise ratio, we talked about the B0 parameter initially in our first slide, where it was proportional to square root of B0. So signal is of course proportional to omega naught squared, but it turns out that the resistance that you saw in that expression is also related to the frequency of operation, where at what frequency you are operating. So at medium frequencies, I think the limit here is 0.5 Tesla, I think, approximately. So that less than that, anything less than that is considered medium frequencies. Anything above that is greater than mid frequencies. So which is what we are in right now in 1.5T and 3T. So in that, the R effective is proportional to omega naught squared, meaning the resistance. Remember the expression right? So it's this R that we're talking about. So that R effective is proportional to omega naught, but in this case it's omega naught squared if you are greater than the mid frequencies or medium frequencies. So now, as you know, this is proportional to sigma squared. So, well, if you take the square root of that, this is proportional to, so sigma, then this is proportional to omega naught squared, right? So sigma is proportional to square root of that, so sigma is in turn proportional to omega naught. You can see that? So that's given here. So that's given here. So sigma is proportional to omega naught in this range, where we are at about in 1.5T and 3T for imaging frequencies. So signal to noise ratio. Signal is proportional to omega naught squared. Noise is proportional to omega naught. So signal to noise ratio is proportional to omega naught. So that's omega naught squared divided by omega naught, right? So signal to noise ratio increases with field strength linearly, not as a square. So that's why if your signal to noise ratio is 10 units in 1.5T, it's not 100 units in 3T, it's only 20 units in 3T. So, but still that linear increase is quite a big incentive to go to higher field strengths. Now going to higher field strengths also has few other effects, simultaneous effects going on. So you have longer T1 relaxation effects and shorter T2 and T2 star effects. So that helps you to keep your we'll see how that helps you in terms of your imaging experiments, or how that creates a problem for you in the imaging experiments as well. So but essentially this is these are the simultaneous effects that are happening as a function of field strength, and you want to keep these in mind when you do your experiments, imaging experiments, to make sure that you're not losing up too much in terms of your signal to noise ratio. Now, so basically this figure is quite complicated. Well, actually, I did not come up with this. This is one of, you will see, Yung-Chon actually created this. So he's basically the summary of this is essentially to say that you change one parameter. It is a mesh, not mesh, but mesh. So you change one thing, it is linked up to something else. It will also change the other parameter. So and if you see here, it is also dependent on T2 and T2 star, because if you change your TE or TR of your experiments, then your signal strength and your contrast is dependent on that. So so the summary, I mean, the take-home message from this is that, well, if you change one thing, you better know that what is its relationship, how does it change the other parameters in your experiment, both from a signal to noise ratio point of view as well as contrast. Well, contrast part we haven't come to yet, but we will see that in the next few slides. So here all the parameters that are so for example, these are the ones that you can change. Well, T1 and T2 are tissue properties, so you can't change that. All the other parameters are something that you have control on, and all of these will have ultimately an effect on either the total imaging time or your signal to noise ratio. So beware when you change something. You better know how it's changing the other parameters essentially. Okay, so since all of these have an effect on the imaging time that you're going to take to collect the full data or your case-based data, so you want to make sure that you are optimizing your imaging experiment to ensure that basically you're doing the optimal experiment that you can under the given experimental parameters. So imaging efficiency per unit time is something that people talk about, and you can calculate that by looking at or evaluating the signal to noise ratio of the voxel per unit total imaging time. So that's typically to do with when you change your TR. For example, let's consider the situation where you want to do a short TR experiment versus a long TR experiment, or short TR experiment with multiple averages. So let's say your initial TR was, so look at this expression. Okay, you can reduce your number of acquisitions to this is equal to 1, and you reduce your TR down by 2. Let's say your signal doesn't quite go to half. Then in terms of your signal to noise ratio, well, noise doesn't change between those two experiments. So in terms of signal to noise ratio, if your signal actually doesn't go to half, even you half your TR or reduce your TR by half, then by doing that experiment with a shorter TR per unit time, even though now you're going to take half the time to collect the data, but then your signal to noise ratio is not quite half, right? So so what I'm talking about is, so let's say TR now is TR by 2. Now signal as a function of TR doesn't quite go to that, but it's, let's say, 3/4 of signal, right? Noise in these two situations remains the same in these two experiments. Then basically your signal to noise ratio in the original situation was, a signal to noise ratio is this, per unit time is basically n times TR, whereas this is sigma. So that's 3 by 2 times S by sigma. So signal to noise ratio per unit time efficiency. Although the absolute signal to noise ratio is going to be lower compared to your original experiment, but your signal to noise ratio per unit time efficiency is higher. So you want basically when you're designing an experiment, you want to make sure that you do that such a calculation to see, okay, am I spending my time efficiently when you're doing such an experiment?
The noise is same both.
Right. So noise in this case is a function of bandwidth. Nothing else changed except for the TR. Right. So, well, in a typical experiment, noise is a function of bandwidth and your number of data points, etc. None of that changed except the TR. Right. So in fact, actually, it is done per unit square root t, square root time, not particularly tr. And I think that's to do with it's the proportionality of the signal to noise ratio per square root of sampling duration, I think. Right. So okay. So the implication here is that yeah. So either, so this is one example where at half TR is not quite going to get your signal to half, but the other example that's given in the textbook is basically a lower resolution image. You're going to take half the time, as long as you're okay with because it's your NX, let's say NY is half in the phase encoding direction. So your resolution along the phase encoding direction, your voxel size, meaning your field of view is the same, but your NY is NY by 2, let's say. And that means your voxel size is increased by 2, everything else remaining constant. Right? So that means you're taking half the time, half the resolution along the phase encoding direction. So now the question is, and so obviously the signal to noise ratio efficiency per unit voxel has doubled, right? Time is halved. Well, it's square per unit square root time. Sorry, so that's basically 2 square root 2. No, that's square root 2. So 2 divided by square root 2. Sorry, I'm sorry. So that's square root 2 better, right? Your signal has doubled because your voxel size has doubled, whereas your time has halved, right? So actually that is 2 square root 2 because that's t divided by 2, right? So that's under square root 2. Everybody following me on that? I'm just, right? So let's just consider 2D. So now what I'm saying is this divided by 2. Okay, nothing else changing. Oh, sorry, not this divided by 2. I'm sorry. This multiplied by 2 and y divided by 2. Okay. So what is your SNR going to be? So that's square root 2 better, isn't it? Okay, that's SNR square root 2, the original SNR times square root 2. Now your total imaging time is NY times TR originally. Now it is NY by 2 times TR, right? So then I guess this per unit square, so SNR per unit square root time, total imaging time, is square root 2 of the original SNR naught divided by NY times TR by 2 square root. So that's twice, not 2 square root 2, I'm sorry. You guys follow? Okay, so that's twice, not 2 square root 2, so I made a mistake there. Okay, so that's portion of efficiency. So if you can, if a low resolution along the phase encoding direction is acceptable, then in terms of SNR per unit time efficiency, then you should just do the low resolution experiment. So that's kind of how you basically it's a question of optimization for your application. Okay, so now we have basically talked about signal. Now contrast is what is more important, because the whole purpose of doing imaging is essentially to be able to distinguish one tissue from the other, or diseased tissue from the normal tissue, etc. So without any contrast, then any image is just not particularly useful. You can't see anything there, right? That's either too dark, that's either too bright, so you can't really see any feature. Well, too dark and too bright is not the question. You can create an image like that where there is no contrast, which is absolutely not useful when, but the fact that just creating an image is not useful is what I'm saying. So ideally you want to create an image something like this, where you have enough contrast to see the features of the tissue that you're imaging. Now you will be able to see or make out that contrast when you so the parameter that you want to look at when you in the presence of noise is not just the signal difference between two tissues, but the signal difference relative to the noise that you have in your imaging experiment is what allows you to be able to distinguish one tissue from the other. So that's called the contrast noise ratio, and this kind of research has been done originally, I think, in television field, where they wanted to look at how well can you distinguish an object in the presence of noise. What should be your minimum signal to noise ratio or contrast to noise ratio between two objects to be able to distinguish that these are two objects in the presence of noise. So originally, if there was no noise, it's just a signal difference, but then in the presence of noise, it's the ratio that becomes the important. So signal A minus signal B divided by sigma naught, assuming signal A and signal B have the same noise standard deviation. If you have different noise standard deviations, then that's SNRA minus SNRB, which includes SA by sigma A, SB by sigma B. Is that clear to you guys? Right, so that's the contrast noise ratio. Now, so visibility is actually something that you can quantify whether an object would be visible. There's a criteria for it to be which provided if it's satisfied, you will be able to see. You can understand that by looking at the two Gaussian distributions here, and the expression given here is actually showing two things. One, the contrast noise ratio can be improved by number of averages, essentially basically because you're decreasing your sigma naught by square root n acquisitions, square root n averages, or if you have a large object. So when you have a large object which is uniform intensity, then each of the voxel that you're reconstructing from that object is an individual measurement from the signal from that object, right? So when you draw an ROI within that object which is uniform, then each of that measurement each voxel is a single measurement. So you're essentially the number of voxels is the number of measurements that you have. So that's why it is square root of n voxel. So even though your noise is, you will see in the next experiment, next couple of slides, if you have a large object, reasonably large object with a low difference between, the intensity difference between the noise, its signal distribution and its noise distribution is, let's say, not 4 sigma naught, but something less than that. But you have large number of points, then this you will still be able to make out that object. The point I'm trying to make is you will still be able to make out that object as an individual object, because your eye automatically averages your signal from that structure, and you're able to see. You saw that example where we subtracted the two consecutive phantom images, and you were able to see that this object was there, even though everything was noise. Do you want me to go back to the signal, or you remember that, right? So you guys remember that image that we should just looked at, I guess. Okay, we can go back. It's not that far away, so. Oh yeah, you're right. Well, let's see. Okay, that's the one. So you can make out that circle, right? So your eye is automatically averaging it. So you're able to see that circle relative to the noise. The noise distribution in the background is Rayleigh distribution. Noise distribution within the object is Gaussian distribution. So the mean of the noise within the object is 0 once you subtract it out, whereas the mean of the noise in the background region is not 0. So because this circle object has such a large region, you're able to kind of distinguish that with respect to the background visibly. That's because of the number of voxels. That's the point I was trying to drive at. Okay, let's just jump through. Okay, so yeah, we're back. Okay, so that's what this particular expression is talking about. So this is temporal averaging, this is spatial averaging basically. So your eye is automatically doing the spatial averaging, but you can also do that manually and then kind of do the distinction between that tissue and the surrounding tissue. So what this particular curve is talking about is, well, let's say you have two tissues and each has a Gaussian distribution of noise around it. So its mean value is SA and SB. To be able to distinguish that these are two different objects, you need to have the separation between these two distributions. Remember, this is not a spatial image I'm talking about. It's the histogram of the intensities of the two objects that we are plotting here. It's not an image of those two objects side by side. It's just the histogram of the intensities. So the histogram of that intensities, if they are separated by 4 sigma naught, where we are assuming that sigma naught is same for these two distributions, as long as the separation is 4 sigma naught, you will be able to distinguish them, because if you guys remember, the area under the curve on one side is like 67% on either side, and then with 1 standard deviation, and then 2 standard deviation is like 92%, and then 3 standard deviations is 97%, I think 97.25% or something like that. So with 2 standard deviations here, the area remaining in this tail is about 2 or 3%, and then the area remaining here is 2 or 3%. So basically the chance that you would make an error of an object which has an intensity somewhere, a pixel which has a certain intensity, that you would associate that with a different object, the chance of that error is quite small, 2 or 3%, or in fact less than that actually, sorry. Yeah, it's actually 0.2% if I remember correctly, but if you consider that separation to be 2 sigma on one side, so that's 4 sigma total between the two distributions. So this actually is called the Rose criteria, where the contrast noise ratio, or the SNR differences between the two objects, is, if it's approximately between 3 and 5, you will be able to distinguish the object. So this becomes important when you're talking about, when you're trying to optimize, let's say for a given imaging settings, the contrast between say gray matter and white matter. Or yeah, so here gray matter has a very low number of voxels in any given slice, whereas white matter has quite a few voxels. So you can actually take that into consideration as well in your imaging optimization of your imaging experiment, to say, okay, if my signal to noise ratio is so much minimum, then I can distinguish white matter from gray matter. Well, this is this is taken off in the textbook again. So you just plotting basically circles of different intensities as we go along in this direction, and different sizes as well. Actually, different intensities as we go along the diagonal actually. So lower intensity, and as we go along this direction, it's higher intensity. So, and the size is also is opposite, basically size is going down in this way. So it's different signal to noise ratio that's plotted here. Signal to noise ratio 1. These have the same intensity, whereas the object size is different. These have lower intensity, object size is same. Okay. So if you look at the same intensity but object sizes are different, lower, so you can, with an SNR equal to 1, you're able to make out this object, whereas you can't make out these objects which are 1 or 2 voxels wide. That's because of that averaging effect that you saw earlier, where your I is automatically averaging the value and then doing that square root n operation. Now similarly here, if you have a lower intensity, even though your object size is big, you're barely seeing that object because the signal difference is quite low. So both are important, signal difference as well as your signal difference relative to the noise and your object size. Both are important for you to be able to distinguish your object relative to the noise in this case, and the same goes for relative to another object, surrounding object. So, well, that kind of summarizes the concepts of contrast, noise, and signal to noise ratio. In the next class, we are going to talk about contrast mechanisms, but I think we're almost. It's already 5:20, so I think we'll conclude our class today here. Sorry? Too many questions? It's pretty low. Anything greater than 3:1 is acceptable, meaning it's just barely there. Anything greater than 5:1 is reasonably good. Greater than 10:1, anything greater than 10:1 is it's very good basically. So typical SNRs of your images today is 20:1 or higher. You won't go any lower than that typically for clinical imaging. 20:1, yeah. But when it comes to quantification and you want to do some high resolution imaging, then you would have to, these SNRs of 5:1 and 10:1 become practical for you because you can't afford to do low resolution, and with high resolution you won't get as much signal to noise ratio. You will always lose some signal to noise ratio. So yeah, that's the trade-off. Yeah. Any other questions? So well, I think I can give you your exam papers next week. I mean, sorry, next Thursday. You'll get your exam papers back. Any other questions? Okay, thank you.